Okay, good morning everyone. This is your introduction to the video for the workshop on correlation and regression for ENVT3361, taken on location in the lab just before we start. Okay, everybody's here, Melda over there. See you soon. So in this week's workshop, we're just going to have a look at correlation and regression for the first time. We'll come back to this in the following week. Before we start, if you really want to use Excel for transforming data, we can use the if-error function in Excel. So I'll just outline how you might use it here. Obviously, if we try to take the log of a negative number, we get an error in Excel, but we can trap that error if you like and say if the result gives an error using the if-error function, then output something, and the most sensible thing to output would be the text string NA, which is our missing value code in R and RStudio. Might be useful. Okay, so correlation, just a word about correlation and regression. We're looking at relationships between variables, and you've probably heard this before, but we can't use correlation or regression to prove one thing causes another. All we can show that is that there is a relationship for various reasons. And you might want to look at the graph at bottom right here, just to, I guess, help you understand that causation doesn't always exist, even though the correlation is quite good. And there's plenty of that sort of graph around. Okay, correlation and regression. Correlation is really just looking at the relationship and how close or not the relationship is. Regression is really when we're trying to predict one thing from another. So the mathematics is similar, and we use R for correlation in Pearson correlation anyway, and R squared for regression. But they are quite different techniques, and as we'll go deeper into regression, you'll find out that there's quite a lot more to it. Okay, so types of correlation coefficient. So the one that we're used to calculating is the Pearson's R, and that's kind of the default that is used in things like Excel to look at correlations. We need to have normally distributed variables to calculate Pearson's correlation coefficient, and sometimes, as we've seen already, we don't have normally distributed data, so we need to use another type of correlation, and that might be Spearman's, which we'll use in this unit, or there are some others as well, like Kendall's tau coefficient, which are based on Spearman's in particular, based on ranking, and doesn't depend on the distribution of the data of the variables that we're looking at. Okay. Example of Pearson correlation for transformed and untransformed data. And in this case, for Pearson correlation, the transformation or distribution of our variables actually makes quite a difference to the observed correlation coefficient. So with this example here, with obviously positively skewed variables, we have quite a high correlation, but just because of the size of the residuals, the deviations from a line of best fit, if you like. But when the data are properly transformed, we can see the spread in the data. The data are now normal, so they fit the assumptions for Pearson correlation, and the correlation is a bit lower. Spearman correlation, though, on the other hand, depends on ranks, so it doesn't depend at all on whether the data are transformed or not. You can try this in our exercise later. And so we'll deal with that in the second half of this video. Here's an example from the Hubbard Valley. So we've got trying to assess a correlation. I know that I've plotted a line, which is technically a regression line, but that's just to illustrate the procedure. Okay, so exchangeable cadmium and exchangeable zinc are obviously highly positively skewed variables, and when we calculate the correlation between them, we get Pearson's R as 0.9. That's a very strong correlation, but it's obviously highly influenced by one or two points. In particular, this point at row 174 up here, which is pulling the correlation and allowing the R value to be 0.9. If we transform our data correctly, not only can we see a little bit more about what's going on, but the Pearson's R value is still a strong correlation, moderate to strong correlation, but has a lower R value because of the spread of points now. Okay, so we can see code for both the correlation test, this thing here, and the graph down below. Correlation matrix, we'll go through this in the video. They're fairly straightforward to calculate. You've probably seen those before, where we calculate the pairwise correlations between every possible pair of variables in our data, or we can select a list, as I've shown in the example above. There are a couple of versions of this that we'll have a look at, and another thing we can do, particularly to check a correlation matrix, and we should always check correlations graphically and regressions and correlation matrices for skewness and the possibility that we have a real relationship that's nonlinear, or in the case of, for example, this example here, where we've probably got two groups of data with their own relationship, but the correlation is assuming that the relationship is across the whole data set, and it just doesn't make sense. Okay, so there are a few checks that we can do. Correlation matrix, I don't know why I've got that again. Okay, I do. I beg your pardon. We can calculate p-values within a couple of versions of the correlation matrix function, rcore or rcore adjust, and we can then look to see whether there is a significant relationship or not. In other words, can we reject the null hypothesis? Or we can do them one by one using a simple correlation test, which also generates a p-value for the probability of getting the relationship in our sample that we see if the null hypothesis is true. Okay, just a word about complexity. So Occam's razor is this ancient statement here: plurality should not be posited without necessity, meaning we don't need to make things more complex unless we really need to. It's not to say that a complex explanation is not necessarily the best. It just means if we don't need to use complexity, we should always err on the side of simplicity. Meaning a simpler model is better than a complex one, all other things being equal. Okay, here's kind of an example that shows that, and I think I may have shown this before. Some work I did a long time ago looking at gold extraction versus pH. There seemed to be quite a consistent relationship across a wide pH range, but then if I looked at the data by, in this case, mine exploration prospect, there was a different relationship for each prospect. So that bothered me quite a bit. And the explanation for that was that the pH itself is a bimodally distributed variable. So my regression relationship was invalid for that reason. And what would make more sense is if we had a separate relationship for each mode or part subpopulation of the pH distribution, which is what I did, and that made a lot more sense. We have a pH group of low pH and a pH group of high pH. Okay, getting a little bit more advanced, we can do different sorts of regression modeling. So let's have a look at the simple and more complex forms of that. One of the useful things about scatterplot matrices is that they allow us to generate ideas or hypotheses. So I'm just going to zoom in on one of the plots within this and have a look at the relationship between lead and iron. Okay, and here it is blowing up here. So we've got lead as a function of iron. Often trace elements are dependent on iron to some extent, and these are in sediments from the peel area in different environments. Channel, which is an estuary, drain, drain's a drain, the estuary itself, outside channels, and an inflowing river. What we actually see is that the drain sediments behaving quite differently there. So a single, simple linear relationship has a relatively good fit to the data, but it doesn't account for the difference between one of the groups. So there's stuff that we can do about that. And then that shows a separate regression line for each group, in which you can actually calculate in R. All right, so first of all, a regression versus a linear model. You can kind of do both in R, but they're both based on the LM function, so they're both pretty much the same. And so what I'm going to do is just explain some of the output from that. The first thing we notice is the statistics of the residuals. So for a very well fitting regression model, we should have the residuals being normally distributed and having a mean of 0. And we can show with some diagnostic plots later on whether that's the case, but this shows us roughly what the central tendency is, and the mean probably is around 0 given that the median is as well. Okay, then the other thing that we get are the coefficients, or the properties of the regression line itself. It has an intercept and a slope, so we can draw that regression line on our graphs if we want to. And we have some statistical tests down the bottom piece of output. And the thing that we're usually interested in is this R-squared value. Obviously, the regression is highly significant, so we can reject the null hypothesis of no relationship. But what we generally look at is the adjusted R-squared value, about 0.44. So 44% of the variance in our dependent variable, which is log transformed total lead, is explained by the variance in log transformed total iron in this case. So just under half of the variance is explained, and the rest of it is due probably to random error or factors that we don't know about. What we can do is actually use a grouped regression. So I'm just going to flick up a couple of slides, and this really relates to this graph here, where we have a different slope and intercept for each group of data separated by a factor. Right, so let's have a look at that output. It becomes a little bit more complex. The syntax for setting up the group regression is just to use the multiplication symbol for our factor, right, within the regression expression. Don't worry about the names of variables or the data set. That's just an example. Using you can do this on your own with the script that we give you. Okay, so we've got an intercept and slope as we saw before, and this is for the first level of our factor. In this case, it's ENV, or environment, and that was channel. They're in alphabetical order, right? So the intercept and slope just refer to the first level in the factor that we're using to divide the data, and then it gets a little bit more complex. We've got a list of intercepts and a list of slopes, and these are the difference between the intercept for the drain and the first level of our factor, environment, and so on. So this is the difference between the intercept for estuary and the intercept for channel. Similarly, we have this list being the difference in slopes, right? So intercept of minus 0.15, and the difference between that slope and the one for drain is 0.15. So they have similar slopes. And if we go back to the graph again, we can see that our channel, which was our first level in the factor environment, has a lower slope than the next category, which is drain, this one down here. So slightly lower. That's a difference of 0.15. let's flick through back to all right, and there's a larger difference. Remember, the other two lines had greater slopes. So if we add these terms to the first two, one by one, we get the different slopes and intercepts. And again, we've also got some statistics related to each coefficient, if you like, and not all of them are suggesting a significant relationship, but we do have a higher R-squared value. So we've got a more complex model, but it explains more of the variance in this case log transformed lead by using log transformed iron as a predictor separated by different environments. So in general, the more complex our model, the more parameters we have to explain things, the better the fit will be. It's just a mathematical consequence. So in our first model, we've got two parameters, just one slope and one intercept, and then we've got a model with 8 parameters, 4 slopes and 4 intercepts. And this should give a better fit, but do we really have a better model, or is it just more complex? Well, we can check a few things, and we'll look at these diagnostic plots in our script when we go through that. But how do we compare models? Well, we use the base R function ANOVA for analysis of variance, and our two objects that we're comparing in our analysis of variance are our linear models. One is the ungrouped, one is the grouped, and our null hypothesis is there's no difference in explanation power for the models. With a low p-value, as we see down here, we can reject our null hypothesis. So actually, in this case, our more complex model is better, even accounting for the complexity. Useful to know. All right, so this is what we're going to do today. This will be on LMS as well as in this video. And just to note that this only gets us partway through correlation and regression. We'll deal with some more topics, generally to do with advanced regression next week, and then there'll be a short report on the topic. Okay. Here we are again. So we're going to have a look at some of the R procedures involved with the first part of the correlation and regression workshop, and we'll perhaps go fairly quickly through some of this because you've got other supporting material as well, and this is what you'll do in the lab yourselves anyway. So what we're going to use is the SV2017 dataset that will not appear in your environment unless you've actually imported the CSV file. So you can see I've got it somewhere in there, you get the idea. But we'll provide the CSV file on LMS for you. You'll see it there. All right, so within that dataset, we've got analysis in the the Smiths Lake and Charles Verriard reserves for a range of elements and other things. We're going to have a look at just checking the distribution of some variables first. So we've got cadmium and zinc in the data set, but I'm just going to make a log transformed version of those as you've done before, and then we'll run the Shapiro test on the untransformed version and transformed. Did I do something wrong there? Yes, I pressed the wrong button. Okay, so untransformed version, we can reject the null hypothesis that the distribution is the same as normal, but not with the log transform version, so that's appropriate to use in a procedure like Pearson's correlation. And similarly with zinc, run low, run higher p-value above our 0.05 threshold. Passes, if you like, the Shapiro-Wilk test, and so those are both valid to use in a Pearson correlation, which assumes normally distributed variables. So with the function core test, we can run that correlation test and get an R value for the relationship of cadmium and zinc. So for correlation, it's going to be the same whether we run
zinc first or cadmium first, it doesn't really matter. Alright, and so with untransformed, which remember wasn't that valid, we get a correlation coefficient from our Pearson correlation test of about 0.75, but with correctly transformed variables, we get a bit of a lower correlation coefficient, so about 0.67 this time. And notice that the p-value associated with that allows us to reject the null hypothesis that there is no relationship between those two variables based on the subsample that we have in this data set. All right. We can also, for poorly conditioned, that is non-normally distributed data, we can use the Spearman Correlation test because that doesn't require our variables to be normal. It is based on the rank of the data within the variable rather than the actual values themselves. So it should be independent of any transformation. So let's try that first with the untransformed variables. Run that. And then with the transform variables. Okay, so ignore the warnings there. We have a Spearman's rho, which is our correlating coefficient of about 0.65. So similar to what we got with Pearson's, but that's not always the case, and they're not strictly comparable. But we can reject the null hypothesis of no relationship, and then running that with the transform variables, we get exactly the same value. All right, and it should be the same p-value, which it is as well. All right, so moving right along, what we can actually do, if we set up our graphical parameters to how we want them, we can plot these things. Let's get rid of the environment altogether, we don't need to see that. And here's a plot function, and we're adding a legend as well. All right, so let's run the whole thing together and I'll explain bit by bit. So we run that. Okay, so we've plotted using base graphics. So remember that if we want to have a range of plot characters, we need to match the number of characters to the number of levels in a factor, so that we'll sort by the factor levels. In this case, we've got sample type, which we can see over in the graph here as sediment, soil, or street dust, so a 3-level factor. So we've got 3 different plot characters, 3 line widths, and 3 different colors. Remembering that we set up the colors in our color palette here, because at least I don't like the default colors. Then we plotted what we call an AB line. An AB line can accept as an input argument a linear model of, that is a line of best fit, if you like, of log transformed cadmium versus log transformed zinc. And we did that even though we didn't have log transform variables in our plot function. We did log transform the axes using log equals xy in quotes. Then we simply add a legend, giving it a position, matching the plot characters and colors and line widths and so on to what we used in the graph so that they match up nicely. Okay, so that shows the correlation graphically with a bit more information there to show how the data is spread between different sample types. What else are we going to get you to do? Well, correlation matrices are quite useful, seeing the correlation between possible pairs of variables, and we do it in a couple of different ways. I'm just going to minimize that graph for now. So we can do it with a couple of functions, either this one here, rcore, which is in the package hmisc, or we can use the version in rcmdr-misc, which actually gives us adjusted p-values, which have a small upwards correction to them to reduce the risk of what we call type 1 errors or false positives, meaning that we fail to reject the null hypothesis, even though it may be true. All right, but they both give similar output, not exactly the same. So what we're doing here is we're creating an object called core table, and we're putting into that the results of the rcore function. That is, this core table will contain our matrix of correlation coefficients. So let's do that. We run that function. Okay, what did I do there? I forgot to load the package. So let's try that again. All right, so what did it do? Nothing. Okay, it didn't show anything here because we actually put the results in this object. And one of the ways that we can display the object is to use the function print. So that's what we're going to do next. I'll actually maximize that window for a moment so we can see the output. All right, so this is our table of correlation coefficients. We've got ones on the diagonal where each variable is correlated with itself, so it has a perfect correlation of 1. And we see some different correlations of different sizes. So for example, the correlation between lead and pH is 0.13, very low, probably no relationship at all, whereas the correlation between pH and calcium has an R value of 0.68, so that's a moderately strong correlation, and there are some other values here and there like that. For example, the correlation between cadmium and zinc that we just looked at, an R value of 0.65. Okay, the next subtable just gives us the number of observations that were compared in each instance. So for example, 94 observations contributed towards generating pH correlation, and numbers differ here because each column has different numbers of Na or missing values. And then we have a probability associated with each correlation too. So a probability below 0.05 enables us to reject the null hypothesis of no relationship for that correlation, meaning that the correlation is significant, but a value above 0.05 means that we can't reject the null hypothesis, and therefore we can't assume there's any relationship at all. All right. So you can have your own crack at running the other version of that, and I'm going to move on to something else, checking our correlation matrix graphically. And the most obvious way to do this is make a matrix of scatter plots, and we have done that already. We have scatter plot matrix. So scatter plot matrix is in car, so we need to run car. I'm going to make the car palette the same as the palette that we set before, and then I'm going to run all of that. Okay, before I do that, let's make the graphics window a little bigger so it all makes a bit of sense, fits on. All right, so there's our scatter plot matrix, and we can see it looks a little messy. Let's zoom that out a bit and put it in a big window. Sorry, but I am getting in the way there, so bye-bye Andrew for a moment. Right, so you can see along the diagonal it identifies the variables that are involved, and we've put formulas in the scatterplot function, which makes it a little bit difficult to see what the variables are, but we can just see them at the right hand side of each label. So anything, for example, in the pH column has pH on the bottom axis, and in the second row down has aluminium on the vertical axis, then calcium, and then cadmium. So this row here has cadmium always on the vertical axis, and so on. So this gives us an idea about our correlations. And it can be, well, it's always useful to plot things graphically if you run correlation analysis, because you can get some odd things going on. First of all, particularly if we run them with groups here, we can see if the correlation holds between different groups. And so, for example, for the relationship between aluminium and calcium, we note that in some cases the relationship for different groups is different. And this is quite extreme. It seems to be a negative correlation for some of the observations, and I think they represent sediment, and a positive correlation for soil and street dust. So that would maybe create some more research questions than it actually answers. But for other things, like the zinc to lead correlation here, with a pretty consistent positive slope for all of the subsets of the data. So let's get rid of that for the moment. adjust the proportions of that just for fun, so we can run scatter plot matrices like that. All right, so that's kind of dealing with correlation. And the next thing we want to do is have a look at regression, right? Notice that down here on our source window, because I've put at the end of some of my comments 4 hash marks, they are interpreted as headings, so I can actually use them to navigate. Right. So what am I going to do? I'm going to look at, because I'm interested in it, the relationship between iron and chromium, but not as a correlation this time. We're going to use regression, which is more of a predictive relationship. So what we're going to do is use regression to set up a simple model to try and predict chromium concentration from iron concentration. All right. So get rid of the graphics window for now. We're going to create transformed versions of iron and chromium in our data set, and then I'm going to run a simple linear regression model where it's just chromium dependent on iron, both log transformed, and then summarize that model. Okay. And let's have a look at what we got. Okay, first of all, what is the output? Just tells us what we did. I guess it's useful as a check. The residuals for the model should have a mean of 0. They kind of do. We can check that a bit later on with what we call diagnostic plots. Here are the estimates of our coefficient, our intercept of minus 1.3-ish, and slope of about 0.62 for the log transform variables, and our indication of whether those fitted parameters are significant or not. Okay, whether the null hypothesis is that they're 0. This allows us to reject the hypothesis that they're 0, and that's particularly important for the slope, of course. A non-zero slope means dependence, and we have an adjusted R-squared value of about 0.41, which means that iron can explain about 41% of the variance in chromium when we've transformed the variables by a log transform. And the overall p-value quite low. We reject the null hypothesis that there is no relationship. So we could use this as a predictive relationship, but remember that we're only explaining somewhat under half of the variance in chromium with the variance in iron. It's not a perfect model for predictive purposes. How could we make it a little bit better? All right, well then, because we know that our data are grouped, that we have several different sample types contributing to those variables, we could run a model by type. And the way that we do that is to set up our linear model using the LM function, have our 2 variables, chromium, wiggly line dependent on iron, then use a multiplication symbol, the asterisk, to multiply by a factor, and that's now our linear model. It means chromium dependent on iron, but a different relationship for each sample type. So let's run that and check our output. Maximize that again. Okay, so you need to go to the kind of PowerPoint-like material earlier to enable you to interpret these. So the first intercept and slope are for our first level of the factor type, which is sediment. And then these represent additive differences between either the slope in, where are we? Okay, in this case, these 2 cases, and the intercept in these 2 cases. All right, we have an improvement in R-squared, not a huge one, and we have a p-value which again enables us to reject the null hypothesis. That's not actually true for all of the parameters, so keep an eye on that. Let's get our code back, and we can compare the 2 models with the null hypothesis that they both have the same predictive ability, noting that the by type model is a more complex model, so it needs to be significantly better because it's got more flexibility in being able to predict. So let's run that and see what we get. We actually get a probability value from the analysis of variance of 0.001, meaning that the more complex model does in fact give us significantly better prediction. Well, that's useful to know. All right, moving on. Diagnostic plots for regression. Well, probably the first thing I'd do is create some scatter plots. Okay, I didn't make a heading there. We can do that. Simple scatter plot. Okay. Oh, it's just in the compare two models thing. All right, never mind. I'm going to put two graphs side by side. Remember that we do that with mf row equals C12, one row by two columns. And you're probably getting familiar with the rest of the parameters as well. Okay, and then I'm going to create a simple scatter plot. Just plot chromium versus iron. I'm going to add a little bit of text, make it one graph A and one graph B, and I'm going to add an AB line or a straight line based on the regression model. Okay, so let's run all those things. It's giving me a weird looking little graph because we're trying to fit two in a pane and my graph's area is too low. So let's make that a bit wider, and there's the graph that we hope we would get, and we're going to run it again. But this time we're separating the data by type. You'll need to look at your version of the code to inspect that further, and also add the lines. I'm using a loop to do that. You can have a look at that code too. So let's run the whole lot, and we put a legend on the graph as well, and then we go. Okay, so that's another useful way of checking the results of your regression model to see that they make sense and that you can calculate slopes and intercepts and things correctly. But one of the things that we should do when we're checking regression models is to use our diagnostic plots. So if we apply the plot function to a regression object, remember that was the output of our linear model function, we should get a set of diagnostic plots. Let's make that a little bit bigger. So I'm setting, we get 4, so I'm making a 2 by 2 matrix of plots, and then after I've plotted, I'll reset those parameters back. So let's run all of those. All right, and there are our diagnostic plots. And we'll quickly go through those because they're quite useful. So what we should see is that residuals have a mean of 0, and here's a dotted line on the residuals graph at 0. So probably we're about right with that. Is there a significant trend in the residuals? Probably not. The red line is kind of what we call a less smooth curve through there. That there is a little wiggle in it, but it doesn't show a huge amount of curvature, and it's not like very high at one end and very low at the other, so we look all right there. The normal QQ plot, the residuals, so in this case the standardized residuals, or scaled in R, are roughly normally distributed with a bit of deviation at low end, so our predictive ability at the low end may be a little bit dodgy. Scale location rarely gives similar information of the absolute values of the residuals to the residuals versus fitted, so we don't need to go too deep into that. And Cook's distance gives the influence effect of individual points, and really we want a Cook's distance less than 1, and the thresholds for Cook's distance are shown with the blue dotted lines. The outer one 1, the inner one 1.5. We got quite an influential point in row 49, and the influence is calculated by removing that point and rerunning the regression and seeing what difference it makes. So the bigger the difference it makes to remove a point, the bigger the Cook's distance in approximate terms, and we can check whether we've got very, very influential points which we might want to do something about in our regression data set. Okay, and we can of course do the same thing for our group regression model, and we get a very similar set of plots. In fact, in this case, row 49 point does have a Cook's distance value, just it's having an undue effect on the regression, and not really that much improvement in the normality of our residuals, nor the trend and mean value of them. Okay, moving right along. There are a list of things for you to try once you're happy that you've got everything. Okay, and as I said, we will come back to this material next week and have a nice little assignment for you associated with correlation and regression. Okay, good luck with everything.